think we started, right? We started page 18, but we didn't finish it, right? Okay, let me go through what we've done so far. And then we'll kind of pick up where we left off. So we talked about how first rewrite our y prime as dy dx. That's what we did. Get our equations nice and set up so that we can cross multiply, so that we can solve for. We'll get our dy dx's lined up. So get my fractions showing, and then cross multiply. Once I cross multiply, then my next stage is seeing that we are making progress. Our dy dx's are lined up. And then the next question is, do we have full separation of variables? In this case, we do. So there's no need to move anything else around, but it's no guarantee that every time we cross multiply that we're done with rearranging. It's just in this case, we do have all the x's together and all the y's together. Okay, left side is just power rule. The right side, though, we have to go through u substitution with our u value being 3x, and our derivative du over dx equals 3, dx equals du over 3. Okay, and then we go through and take our antiderivative, pull the 2/3 out in front. The e to the u is just e to the u. That's the rule for e to the u. And then we bring back our x. So 2/3 e to the 3x plus c. So we have, we're done with the calculus. This is where we stopped yesterday, right? We did power rule on the left, u substitution on the right. Okay, so let's reset. I'm just going to choose to clean up. So at this stage, I mean, you can do anything you want. You can solve for c or you can solve for y first. I'm just going to clean up the left side. And then once I feel like I have an equation that is suitable for me to solve for c, I'm going to do that, because I would like to get rid of the fraction, but before the square root shows up. So I'm going to multiply everything through by 2. And then distribute the 2 through. I get 4/3. I can take the square root, but I'm thinking, wait, maybe this is a good spot for me to plug in and solve for c, because this is a relatively clean equation. So I'm going to go ahead and do that. So I will insert 0 in for x, 5 in for y. Okay, 2 times 0 is 0. E to the 0 is 1. So that's just leave me with 4/3. I can subtract 4/3 from both sides. Common denominator, I can make this 75/3 minus 4/3. This gives me 71/3. So my C value is 71/3. Once I have my C value, then I'm just going to take this and insert it back where I started making my substitution for X and Y. So I have one more thing left to do. That is to get that Y squared resolved. So what can we do from here? Take the square root. And understand that anytime square root is involved, there's what that's going to show up on the right side. Plus or minus, which means that there are two candidates, but only one of them can be selected for our problem. All right, so how do we know which one to choose? What do we look at? Sorry?
The Y 0 side.
Yep, that's right. What do we look at here? Look at the sign of the X or the Y value? The Y value, yeah. So if I plug 0 in, I got to get a 5 in return. I get a positive 5 in return. The only way I'm getting a positive 5 in return is with the positive square root, right? If I plug 0 in here, I'm going to get 75/3. Square root of 25 is a positive 5. But plug 0 in here, I'll get a root 5 or root 25, but then the negative is going to stay. We want the positive square root. It's based on the order pair. We want something that will actually go through that point. Leave your answer unsimplified. As long as the Y is by itself, that's good enough. All right, any questions?
It's a positive 5.
It's positive 5, that's right. So if it's a negative 5, then you'll choose a negative square root. Guys, I want to kind of change things up a little bit from the schedule. I think what I want to do is do the review or do more practice tomorrow. And I feel like I want to just kind of get the notes out of the way for 5.7. This is inverse trig antiderivatives. If I can get that out of the way, then we can do tomorrow being review and then continue reviewing all the way into next week as well. So let me shift over to the notes for our last set of notes for this unit, which is integrals of inverse trig functions. Okay. So I'm going to swap the days around so I can just push the review. Just have this be the last day of notes rather than tomorrow. So and these are also the last set of integral rules. Okay, so we're almost done covering all the new integral rules. So first semester, we learned about these are the messiest rules, right? There's the arcs trig, has so much pieces going on. We talked about how really first semester it was only 3 rules to worry about, right? Because the arcsine, arcsine, and arccosine are just negative versions of each other. Arctangent, arctotangent are just negative positive versions of each other. Arcsecant, arccosecant, negative positive versions. So we should think if we memorize the first row, we basically have the second row figured out as well. We talked about how arcsine and these all have denominators and numerators. All the numerators are the same. Arctangent is the easiest one without the square root, without the minus sign. And then we move on to the most difficult one, which is arcsecant. To memorize them, we know that the absolute value and u squared are next to each other. So that helps remind me that it's u squared minus 1 and not u squared, not 1 minus u squared. And if I can figure out the order of the square root u squared minus 1 for arcsecant, then I can turn around and I can flip that order for arcsine. Okay, so this semester, we're just working backwards from these rules here. So the antiderivative of this will bring us to arcsine. The antiderivative of this will bring us to arctangent. The antiderivative of this will bring us to arcsecant. However, there's a little bit that's going on here in the sense that it's not always going to be a 1 involved. Rather, it's going to be a that's involved. And the way that we can tell the difference between a and u is your a is your constant and u is your variable. So if I can get it into this form where I have a square root with the constant first and the variable second, that's basically similar to this 1 minus u squared. We know it's going to be arcsine, and arcsine is just going to be u over a plus c. The u is going to be your variable. Your a is going to be whatever you see in here. Arctangent, no square root, so there's no square root. If I can get that a squared plus u squared to show up, I know it's got to be arctangent. But there's a coefficient that's going to be involved here. So 1 over a, arctangent of u over a plus c. And the arcsecant is 1 over a arcsecant, absolute value of u over a plus c. Okay, so let's try some of these examples here. So number 1, we have 5 over x times the square root of x squared minus 9. This looks like, if we're matching the rules here, this looks like it's a best fit with the third one because we see something outside and we see variable followed by a constant. Okay, so we're going to target this 1 over a arcsecant of u over a plus c. So the first thing that we're going to do is we want to identify, we want to rewrite this problem here. So integral of 5 over x square root of, and we're going to force sets of parentheses with squares showing up. So we'll do parentheses squared minus parentheses squared. This is a good way for us to make sure that we're finding the correct a and u value. So what can I insert into the set of parentheses without changing the problem? X, right? Just simply x. Okay, so it looks like there's not much change here. Okay, what can I insert into the parentheses so that this is not changing the overall value of that? 3. So the reason that we go through this particular step is therefore whatever is inside the parentheses is your a and u value, and then you're not getting thrown off by that 9, that you're not picking the incorrect a and u value.
Kind of factor.
We're not really going to factor, even though factoring is going to come into play next page. But right now we're just getting the parentheses to show up so we can pull the a and u value. Now, which one is the a and which one is the u? X is the u and 3 is the a. How do we know that x is the u and 3 is the a?
A is a constant.
Good. A is a constant. So we'll keep reminding ourselves. Okay, how do I know which is which? It's because one is variable, the other is a constant. Okay, so my u is x and my a is 3. Guys, we're on page 23. Now from here, we're going to go through use substitution, and we're going to make our problem look exactly like this, just so that we can have the assurance that we're ready to go, and then we can apply the rule after that. Okay, so if my u value is x, my derivative du dx is what? What's the derivative of x? 1. Just 1. Okay, and I'm going to solve for dx. Dx equals du. Okay, so I'm going to make my substitution here. I'm going to pull the 5 out in front because that 5 is not going to impact us, or that's going to impact the problem. Dx gets replaced with du. My x is my u, square root of u squared minus a squared. Do I have a perfect match with the rule that I want to use? Yes, right? So now we're just going to follow whatever the rule says. The 5 is going to be the first thing because that's a coefficient. The coefficient may not be part of the rule, but it's still something I need to keep. Okay. So 5 times 1 over a. What's my a value? 3. 3, so 1/3. Arc secant absolute value of u, so absolute value of x over 3 plus c. So we leave it in that form. I'm going to make it 5/3, and then the absolute value just stays. Okay, number 2. If we were forced into one of these 3 rules, which one would be the best fit, you think? Because
There's
no square root, right? So that's an easy giveaway. If we're deciding between these 3 arc or inverse trig rules, then without the square root would be obviously the arctangent. Okay, so but first, if we want to get the denominator to be set up, let's force the set of parentheses to show up so that we can, so we're not pulling the incorrect a and u value. I'm going to rewrite the problem here. So I just want to rearrange it in this form so that I'm not, so I'm making sure that my a and u value are correct. So what can I insert for, do with the 4 so that this squared is equal to 4? 2. So that's going to help me with my next step. Any changes here? Same thing, right? X minus 1 squared is the same thing as x minus 1 squared. So there's no need to change that because this is already nicely set up for us. Okay. Anybody, any questions here? Everybody see the process that we're doing? Okay, so now let's identify our a and u value. What's our u value? Because there's a variable in it. Okay, so your u always has a variable in it. And my a value is 2. Okay, once you're here, go through use substitution, and we're trying to get everything in terms of a and u. The hope is that we want to make sure that we have everything. We want it to look exactly like this rule, so that we're certain that we're getting everything lined up. Okay, so what's my derivative? Du dx equals, solve for dx equals du. Okay, let's get everything in terms of a and u. So integral of dx is replaced with du. This is my a squared plus u squared. Now, ultimately, if you get the a squared and u squared flipped around, does it matter whether it's a squared plus u squared or u squared plus a squared? It doesn't matter as long as you know which one is the a and which one is the u. Okay, so it doesn't, one can come before the other. You can flip flop them. Just make sure you know which one is the a and which one is the u. Again, a is the constant and u has the variable in it. Okay, so now everything matches up nicely. no coefficient to keep track of, so we can jump directly into our rule. Our rule is 1 over a arctangent of u over a plus c. Right? So 1 over what? 1 over 2. So 1/2 arctangent of u over a, so x minus 1 over 2 plus c, and there we go.
And arctangent is the same thing as the opposite of something, right?
Arctangent is the inverse of tangent, yeah. But yeah, so so having said that, you can write it this way as well. And that's fine as well. These are equivalent.
Never to solve for the tangent.
No, not to solve. As long as we get the antiderivative, we're done. Okay. All right, number 3. What do you think is a good fit for number 3? And why is that? I know there's nothing outside, but we don't want that to be the way that we determine what else is different between arcsine and arcsecant. Yeah, the constant is the positive term versus arcsecant, the variable is a positive term. So that's the way that I want us to distinguish that. So number 1, the variable comes first, the constant comes second. But for arcsine, the constant is first, and the variable is the negative. So we know that we're going to target arcsine in this problem. So let's go ahead and get our parentheses to show up so that we're not pulling the incorrect a and u value. So we'll force 2 sets of parentheses, and then we'll try to fill them in. What can I insert into the parentheses so that 7 doesn't change its value? Root 7 squared is the same thing as 7, right? So I'm purposely doing a step here so that I'm not getting the wrong a value in my process. Okay. So what can I insert in here so that this squared is same thing as 16x squared, 4x.
Maybe it's not a parentheses.
I'm sorry.
So there's not a parentheses, right? That's by sign 16x.
Let's see. What's your question?
Never mind.
Okay. Yeah. So we have to set a set of parentheses here and make sure that whatever's inside here squared is the same thing as that value there.
Yeah, because I know you put the term parentheses, they separate the square from it. So that means you had to bring down the coefficient attached to it, right?
Yeah.
Okay.
Mm-hmm. Okay, so now let's go through use substitution. We're ultimately trying to make this look exactly like our left side before we jump into our rule. Okay, what's our a value? Yeah, we know it's going to be root 7 versus 4x because a is the constant. And our u value is 4x. Okay, what's the derivative? Du dx equals 4. Solve for dx. Sorry, du over 4. Yeah, du over 4. Okay, so let's make our substitutions. Everything, we're hoping that after we make our substitutions, we can make our problem look exactly like this. And if there's any coefficients, we can just make sure we push them out in front. So there's my a squared minus u squared. It's getting close. What can we do to make it so that I can kind of isolate the rule that I want to use. Pull that 4 out as 1/4. Okay. Okay, do I have a perfect match? Yes. So now we want to go through the rule here. Arc sine does not have a 1/a in front, but we still got to keep our coefficient, right? If there's any coefficient, we got to make sure that is included on top of your antiderivative. So the 1/4 is going to come first. There's no 1/a. We can jump directly into arc sine. Arc sine of u over a, so 4x over 7 plus c. Right. And then in this course, we talked about how you don't have to rationalize the denominator. The only time you have to rationalize the denominator is if the multiple choice selection has the denominator rationalized. Then you just have to be able to pick that option. But if it's free response, you don't have to rationalize the denominator, and you won't get points taken off. Okay, question. Okay, so this page, everything is nicely set up in terms of, I mean, we do have to get the parentheses going, but basically we're able to jump directly to finding the A and U value. Sometimes the problems are not as clean as this, and we have to get to this point to be able to pull the A and U value more clearly. So let's go to the next page, and there we have to go through an algebraic step for certain problems to get it into this form in order to pull the A and U value. Okay, so page 24. Okay, and this process is called completing the square. So complete the square allows us to get something like a trinomial into something that is a square term plus a square term. Okay. Let me just walk through the steps here. We're always going to try to get into standard form first, in decreasing order of degrees. And then we add spaces within our expression so that we can find a nice coefficient that will allow this to factor nicely. Once it factors nicely, then we can get that our expression to be like what we saw before, where your variable is nicely self-contained, like this x minus 1 squared. Okay, we're trying to get it into this form so we can pull our A and U value. So we see that our denominator requires that if we want to use arc tangent. Well, first we know it's arctangent because there's no square root. And then, so we're going to step to the side here and just focus on working on that trinomial. I'm going to write that to the side here, x squared minus 6x plus 13. Okay, I want to complete the square here. I want to find a number that will allow for a nice factoring to occur. So I'm going to do this, x squared minus 6x plus space plus 13 minus space. So I want to find a nice value for as a factoring partner, but whatever number that I use, I want to make sure I immediately subtract from it, because ultimately I don't want to change the overall value of this expression. So whatever number I find, as soon as I subtract it, then I'm not changing the overall value. Yes.
I know in direction says like that 13 would technically represent like a C in it, like in the space, but that's not like the C value, right?
Yeah. So the plus C is at the end. Yeah. We're still not ready for anything with dealing with plus C. Okay. So the way we find what goes inside that space is this formula. This is b over 2 squared. So that's what goes into both spaces. Okay. What do you think our b value is? Yeah. It doesn't matter whether you choose -6 or +6, because it's going to end up being squared. So it'll always be a positive number. Well, it'll always be a number that I know there's a negative here, but when we put something into the space, is always going to be just the positive version of that number. Okay, so what's 6 over 2? 3. And 3 squared is 9. So 9 goes into both spaces. So this will factor nicely because what multiplies to be 9 and adds it to be -6? -3, right? It's -3 and -3. And we're forcing, we're causing the factor to be nice in the sense that they're always going to be the same number, and we can merge it into what? X minus 3 squared. Okay. Plus, and then what's 13 minus 9? 4. So now that's reset. Now it's going to be like a problem that we've experienced on the first page. I'm going to rewrite the problem now that our denominator is in a reduced form, or in a form that is useful for us, helpful for us. Now we can basically attempt this problem from the first page's perspective. Okay, so now we're ready to go through our full process, getting our denominator to show parentheses. So basically, we're including a step before our first step from the first page. Okay, so we're doing the complete the square step so that we can get to our starting point that we did on the first page. Okay, any changes here? Same, right? And this one is just going to be what? Yeah, 2 squared, right? Yeah, 2 squared is same thing as 4. Okay, and the whole purpose of us going through this additional step is so that we're not making a mistake with identifying our A and U value. Okay? Because if you identify your A and U value here, you may make a mistake and think that A value is 4. But if we go through this step, then it's more clear, so that we can hopefully remove that that possibility of a mistake. Okay, so our A value is 2, and our U value is x minus 3. Derivative du dx equals 1. Dx equals. So now everything goes into my rule here. I want to make my problem look exactly like my arctangent rule here, or the left side of that integral. So du over u squared plus a squared. Okay, so now I'm ready for my rule, right? So 1 over a. So actually, no coefficients, right? So there's nothing to put in front of my rule. 1 over, what's my a value? 1 over 2. Arctangent of plus c. Any questions so far?
Is those complexes that are going to use it today?
Yeah. Okay, let's do one more. So example 5 is a little bit more complicated than I want it to be. So I want to, sorry, does anybody still need this? All right, so number 5, I want to change this up a little bit. So if you can change the numerator to just be -7, we're just going to do that problem instead. All right, so we know it's going to be arctangent, so we're going to work towards that. But we see the denominator is not favorable for us to pick our u and a value, so we got to go through what again? Yeah, complete the square, right? Yeah, complete the square factory. So I'm going to step to the side here and get that form to show up. X squared plus 2x plus space plus 2 minus space. So basically, we're not changing anything here, right? We're just kind of shifting that over and just making sure that we have a plus space and minus space on either side of that constant. Because I want to find a number that will definitely factor for us nicely. Okay, so our formula is b over 2 squared. Yep, so 2 over 2 squared, which is 2 over 2, yep. So 1 goes in both spaces. We should be able to get this to factor nicely for us. 1 multiplies to be 1 and adds up to be 2. What two numbers?
X plus.
Yeah, x plus 1 and x plus 1, right? And then we can merge it back together and make it what? X plus 1 squared plus 1. Okay, so now we're at the starting point from the previous page. Okay, looks to be a good fit for our tangent. Let's get the denominator to show 2 sets of parentheses. Any changes with the first set parentheses? Still going to be what? And the second one is still going to be 1 because 1 squared is still 1. Okay, so all right. What's our u value? Good. Your u value has the variable in it. Your a value is just a constant. du dx. Make our substitutions. I'm going to push that -7 out in front. Dx gets replaced with du. U squared plus a squared. It matches my rule perfectly. And now I'm ready to apply my integral rule. My rule is 1 over a arctangent u over a, but what comes first? Don't forget about that -7, right? That -7 is not part of the rule, but it is a coefficient, so it needs to be part of my answer. So -7 times before arctangent 1 over a, right? What's our a value? 1 over 1. Yeah, so you're right. Actually, we could have just jumped into arctangent since we don't need that 1 over 1. I just want to make sure that we are looking for that. Okay, arctangent of x plus 1 over 1. I can drop that 1 if you want, because divided by 1 is not going to make a difference. So this is fine. If you want to make it a little bit cleaner, that's fine as well.
So we get +1.
We do, yeah, because we need that entire u value to be in the numerator of my rule. Okay, I do want to point something out here about these types of problems, and it's that, you know, if I didn't tell you that this was arctangent, how would you know? How would you know that that the denominator is not the u value, right? When this is mixed in with all the other types of problems, how can we tell that, wait, this is our trig versus, you know, just a normal u substitution problem? It feels like, you know, that could be a hard thing to do. So I do want to point something out here where you can instantly tell whether this could be a candidate for an arc trig, either arcsine, arc tangent, arcsine, arctangent, or arc secant. And I want to go back to the first page. I want to point out some things where you can look at a problem and tell, wait, this is probably going to be an arc trig problem, okay, versus a normal u substitution problem. Okay, let's go back to the first point. Okay, don't pay attention to the square roots. Just tell me what the degree of the numerator and the degree of the denominator is. Okay, so just ignore all the square roots. Just look at the degree. What's the degree of my numerator here? Wait, not degree 1, degree 0, right? This x is 0 power. And degree here is what? 2, right? Again, ignore the square root, okay? Just look at that. So you see degree 0 versus degree 2, okay? You see how there's a gap there, degree 0, degree 2. If the denominator has a degree that is more than 1, where degree of denominator is higher, like 2 versus 0, or 3 versus 1, or 4 versus 2, that gap of a degree means this is probably a good candidate for our trig. Right. Number 2, do you see that relationship here? Degree 0 versus degree 2. There's a gap with a denominator showing the higher degree. Number 3, degree 0 versus degree 2. That is a gap. That's an arc trig candidate. I'm sorry?
Is that the biggest like thing?
That's the biggest, especially when you're looking at the problem and it looks like just a normal U substitution problem. This is the way that we tell, right? Number 4 here. The numerator is degree 0. The denominator is degree 2. That's a gap. That's an arc trig problem. Same thing here. Degree 0, degree 2. It could be degree 2 and degree 4, okay? But if the degrees are consecutive, then we don't want to, we know that our trig is not going to, it's going to be probably a normal U substitution problem. Yeah.
Did you cross it out? You won't have to go.
Right. This is a difficult one because this one we got to split up into 2 problems. One is a U substitution, the other is an R trig. I won't give you one like that, and that's more complicated than what you're going to see on the AP exam. Okay, so your homework. I'm swapping these days around here. I'll send out a reminder. You guys can find this homework under in your calendar and also in your homework page, and then we'll basically shift over to review starting tomorrow. Okay, all right, come get your phones. Thank you.